two-person team. Truthfully, we spend a ton of time in various labs and coffee shops working on it interchangeably back and forth together. So we really overlap pretty heavily on our responsibilities. So it's interesting that they were right before us because the motivation for our project was also addressing unstable power supplies. His neighborhood tends to have outages through heavy trees, and I'm a sailor, so I'm often out where I'm off the grid. And what we wanted to do was look into harvesting ambient and waste power. And we noticed that there's a lot of solutions out there, but all of them are focused on one thing. So you have a solar panel that's got its own charger, its own intelligence, its own monitoring, and then you plug your phone into it. And then you have, say, a little turbine for your boat, and it has its own system and its own monitoring. So what you end up doing is really duplicating a lot of the expensive part, which is the intelligence and the monitoring and the brains of the system is redone every time. So what we want to do is design a system that could adapt to the varying, the impedances and the input characteristics to effectively use your different sources. Mechanical through a turbine, we used a TEG, a little CPU we picked up just from Fry's, and small solar panels like you would typically see. And the other one that we used that we thought was kind of interesting was both of us have stacks of batteries that we're going to take to recycle. And they're too dead to really do anything, but they still have power in them. And we were interested to see if we could draw enough power to that to charge our system and then use that to charge a cell phone, and that was successful as well. So the last thing that we wanted to do besides flexibility was, because this is an educational experience for ourselves, we wanted to make something that had a bit of educational value while you were using it. So rather than just have a black box with an input and output and a light that says I'm working, we decided to go through and do current sensing, voltage sensing, calculate power, calculate how much sense, and calculate what's currently in the battery, how long it would take with each given peripheral that you've got plugged in at this moment, how long would it take to charge the battery, and give you a way to interact more with the peripherals and see what you're doing. So when you change them around, you can see, oh, if I hold this in the sun, this one works better or it doesn't, and give it a bit of an educational side as well. So you can see the picture up there. So the last thing we did was package it in something nice and sturdy. We figured this is the kind of thing that's going to be taken outside and connected to all sorts of different things, so it's sealed and in a nice stable housing case all bolted down. Of course, if you have a way to collect the power, the next thing you really need to do is, you have a way to deal with the power. What you have to do is collect the power, and that's where Joel's primary focus was on the various peripherals.
Okay. The peripherals that Simon mentioned here, that's the solar panels. This is a little bit hard to tell what that is at the distance, but that's basically a thermoelectric generator that has a heat sink on it because you need a delta T in order to generate sufficient voltage for charging the battery. This is actually the AA battery pack, and this right here, this is not something you buy just off the shelf, but it's from some kit components that were for renewable energy. I basically had to custom design this with these electromechanical turbine. So it's basically right, it's hidden behind there. So you can just hook this up to your kitchen sink, turn on the water, and you get electricity coming out here. And the various regimes of power that we're getting, this is in milliwatts right here. The water turbine was the lowest one, but it still hit our metric of 30 milliwatt minimum peak power. The next one up was the thermoelectric generator, and what I did there was take it outside and use a magnifying mirror on the side, focused it on a black copper panel so that the radiative energy was hot enough to breathe the delta T. Actually, what came in second was actually the AA batteries that were disposed of. The ones that were at like 1.3 volts when you take them out when your device stops working, you can actually still drain quite a bit of power out of those. And since I keep a paper bag full of those things, it's kind of a nice way to use them before they go to the recycle bin. And of course, the easy contender there is the solar power. But any questions?
We have 30 seconds for questions.
So once you've got this energy captured, how do you deliver it? Can you set the voltage? Can you set the control, the output?
Actually, it comes out, it's preset. You have a 1 amp or a 2 amp, and it comes out to the USB spec. So it's got, I guess you can't really see it, but in here there's a USB output that plugs into your phone.
Okay, so it's a USB output.
Right.
Any kind of input, USB output.
Yeah, exactly, right here.
Oh, that's okay.
Oh, sorry.
Okay, well, you're trying to keep 3.3 volts power.
But,
Fine.
absolutely,
Okay, so you're just trying to maintain 5 volts.
right.
What if it goes below 4.5 or something?
In that case, the battery board, it shuts itself down. It basically browns out, it won't be power anymore. Similar to how you do if you were using any other battery-driven systems.
Thanks, Simon. Joel?